particularly for photometry, to understand the photo-Z's, and I think we're going to be hearing about that from Gary and so on. So the next generation, well, there's two generations here. PS1 is now working, has been collecting data for 6 months. PS4 is still being built, and there's a whole bunch of other things being proposed. So Conrad will tell us, I'm sure, about kids, and this is hopefully going to go start producing data or have first light next year. Vista, these are slides that I stole about a year ago, so they're slightly out of date. Vista's now working. The Dark Energy Survey, I think, is projecting to get first light 2012. The Japanese have Hyper Suprime Cam, and there's the LSST, and maybe if you can get Roger drunk, you can find out whether they're going to Astro 2010, will propose that, and then JDAM or something else. And so this is what we've been up to on Hawaii. This is our version of LSST. Someone was asking me, why doesn't it look like LSST? And the short answer is that the LSST design is flawed, and you know, because essentially you're dealing with natural seeing. Right? You're not doing adaptive optics, so it doesn't matter whether you use one big telescope or a distributed aperture thing. What you've really got to do is a trade study of the systems engineering and the pros and cons of what will get you there faster and at the best cost. And this is the right way to go. But of course, this is a cartoon and not a real telescope. But what is a real telescope is PS1 on the beautiful mountain of Haleakala with Mauna Kea, where it'll eventually go in the background. And so the one of the key components of this is a 1.8 meter telescope. Here's a key component, which is the 1.4 gigapixel camera on the back there. And so this was, you know, what we developed this design based on, is that since 1970 or whatever, when these Nobel Prize winners developed the first CCD, they were trying to make a memory storage device, but it didn't work because it was sensitive to ambient light, their lossile gain. The size of these CCDs has doubled roughly every 18 months, or at least the kind we have on big telescopes. And so this shows the size of the collecting area of telescopes on the top, and the green ramp is the number of pixels. So clearly the future is all about technological developments. Just think for a second what this means is, you know, here's on this curve of growth, right? Megacam was 300 megapixels roughly at the end here. The Gigapixel 1 camera is bang on the trend here, that things will double every 18 months. So 10 years from now, when some of us will, most of you will still be active in the field, we will have 100 gigapixel cameras if we want them. Right? So we've really got to think about what to do with that. And of course, LSST is going to look interesting. Here's another couple of views of the gigapixel camera. And this is Lou Robertson, so don't get any ideas about going to steal it, but he's there to set the scale of this thing, where you have the camera, 500 channel electronic system, which can suck the data out of this thing in a matter of seconds. And that itself there's this, you know, interesting technology in how you do all of this. Had we used the state-of-the-art Leach controllers, one would have had a huge room full of devices and a minor power station nearby producing the power. So this shows the scale of Pan-STARRS 1 compared to conventional telescopes where you can image a region that size. This is the kind of size of the Patra Sky 7 square degrees, 3 degree diameter field that the gigapixel camera sees. And so we're going to use this to do everything, of course, you know, looking at the solar system, our galaxy, and the large-scale structure. And ultimately, we're going to have 4 1.8 meter telescopes on Mauna Kea. We hope that other people will join in this endeavor, and there will be more, but this will be the Hawaiian component. The A omega is about 50 meters squared, degrees squared, you know, so about a factor 6 or so less than LSST. that essentially meets the old last decadal review's spec for an LSST, more or less, give or take. And so time domain astronomy for cosmology, of course, is interesting for the supernovae, but we're more interested here in the static science. So let me mention a couple of the interesting features about this and what we've been up to in the last few years getting this working. Here's the optical design. And it turns out that it's very critical to get these optical elements, which there's a primary mirror and a secondary mirror, and these enormous lenses. These all have to be configured to a precision of tens of microns, right? A third of the width of a human hair, right? Otherwise, you screw up the image quality. This is one of the challenges of doing wide field imaging. And the way we do this, we've got hexapole control here. We've got pneumatic supports of this mirror. We can control the shape of this mirror in its orientation. And you'd probably be interested to realize that the way that we do this is actually, would be very, very familiar to anyone who's played around in the field of weak lensing. Because what we do is we actually take out of focus images, but and these are very good for revealing any errors in the optics, and we decompose the shapes of these so-called donut images in a way which is similar, very similar to the way people are applying to galaxies with shapelet analysis and so on. And what we've done is developed a pipeline where we can take an out-of-focus image. We get for each chip on the detector plane about 100 stars, and so we can get a very accurate picture of what the median out-of-focus images say for that chip. And what you see is they're not round. This is when the telescope's misconfigured. If everything's perfectly in collimation, these things will look like round donuts, undistorted, with the hole right in the center. And you see they're not like that at all. They're quite strongly distorted, and the distortion varies across the focal plane. And what we do is we take that data and reduce it to a vector of several hundred components, and then we do a bunch of, standard linear algebra magic, and are able to decompose this into what are the deformation modes of the telescope that will produce just that pattern. And this is a ray tracing when you use that solution to predict what you would have seen, and you can see that it works very well. Once you know what the deformation was, you can fix it. So time's getting on. So it is very much weak lensing. You work in the perturbation theory limit, just as we do analyzing lensing by the gravity in the cosmos. So these are the filter bands we look at. We try to match them to Sloan, but we threw out U and put in Y band as well. We had to develop these big filters in order to do that. They work, however. Must be a big image because it's taking a long time for the next one to come up. We're very concerned about getting to 1% or hopefully better photometric accuracy for the photo-Z's. So we've installed a very sophisticated calibration system which has this screen which we can illuminate with either white light or with a tunable laser that can be scanned, so you can measure the system throughput for every pixel every day. Right? And the idea is that this will help us beat our enemy, which is the atmosphere, right? In doing the photometric pipeline, you're essentially solving, F equals AX plus B, where A is the transmission of the atmosphere, how much it's absorbing the light from your target, and B is the air glow, how much it's adding to your signal. And that sounds pretty trivial, except that A and B are complicated functions of time and wavelength and so on. And so using this calibration screen, we hope eventually when we combine that with a low resolution spectrograph measuring the air glow, we will be able to determine in time for each exposure how much absorption there was, because all of these water bands and so on are varying with time, and this is the way to get the high precision photometry. The detectors have some very interesting features, most notably of which the brainchild of John Tonry, which is to do tip-tilt compensation by moving the lightest part of the apparatus, namely the electrons that are accumulating in the image. And this shows that the quantum efficiency that we went for, which is being adopted by other projects, of course, which is to try and get out to very high QE at the longest wavelengths, because that's where most of the science is. We've developed a real-time image processing pipeline. Currently, it's turning round on, up to 1,000 gigapixel images per night, currently within 24 hours, ultimately within 30 minutes. And the idea is you can combine images, difference them, detect transients, remove transients and variables, stack them all up, and that's what we will use in lensing. But here's an example of acute difference image showing, oh golly, here's two asteroids caught in a tiny little fragment of one of these massive images.